Good afternoon and welcome to this webinar, Operational Excellence in Food Processing Through Simulation. This event, brought to you by Food Engineering, is sponsored by Siemens. I'm your moderator, Deborah Shug, Chief Editor of Food Engineering Magazine. Thanks for joining us. Today's presenters are Dr. Ravi Aghlavi and Tom Phillips. Dr. Ravi Aghlavi is the Director of Chemical and Process Industry at Siemens PLM. Ravi is a chemical engineer by training and received his doctorate from the University of Heidelberg in Germany. For more than 15 years, he has performed advanced engineering analysis backed by CFD and simulation to solve problems in the chemical industry. He now leads the effort of applying CFD for chemical processing applications at Siemens PLM. Tom Phillips leads the Siemens PLM simulation portfolio development activity for growth industries in North America. Tom received his PhD in mechanical engineering from the University of Tennessee and has more than 25 years of experience relating to engineering simulation. In his current role, Tom helps Siemens PLM customers implement simulation into their engineering process to facilitate innovation, improve engineering efficiency, and enhance product performance. Don't forget to submit your questions, and later in the program, our presenters will address as many as possible. Today's event is being recorded and archived on www.foodengineeringmag.com. And now I'd like to turn it over to today's presenters, Dr. Ravi Aghlavi and Tom Phillips.
Okay, thank you, Deborah. This is Tom Phillips, and I'd like to welcome everybody and thank you for taking time out of your day to attend. Ravi and I would like to talk to you, as Deborah indicated, about the use of simulation in the food industry. And I want to start by talking about a trend that I think everybody is aware of, right? So digitalization is everywhere, and it's changing pretty much everything we do, right? So the way we travel from one point to another, the way we listen to music, the way we get our food, there's almost nothing that isn't impacted by this global trend in digitalization. And that includes into the food industry, right? So when we look at how digitalization is transforming, a few different examples here with personalized packaging. The Coca-Cola, their Freestyle app enables you to get on your smartphone and create your own flavors. And then all the way to a master chef in New York City using advanced manufacturing techniques like 3D printing to build chocolate creations for people. So you can see that, the digitalization trend is here. It's impacting the way our products are produced and brought to market, and you as engineers have got to accommodate that in your day-to-day lives in order to, be successful. And it's not all of a positive change, right? So this, according to Accenture, the digitalization is the main reason that just over half the companies in the Fortune 500 have disappeared since the year 2000. And if you think about that trend, that's really astounding, right? So half the companies are either out of business, they've been acquired, or they've dropped out of the Fortune 500, and because of the impact of digitalization. And so in order to survive that disruption and really thrive in this era, there's a lot of change going on, and the change comes, really fast. That, we believe that the incumbents then need to become digital enterprises. You need, and that's more than just adopting CAD or adopting a simulation tool. That's really about taking digitalization and tying it through your entire business. So if I look at this, and that starts getting into the concept of a digital twin and the digital thread. So the digital twin is basically a virtual representation of the product, and it incorporates, it's kind of a single source of truth that you can look at that goes all the way from the ideation stage at the very beginning of the product life cycle through into realization where you're manufacturing the product, and out into utilization where the customer is using the product out in the field. And so if we can create a digital twin and tie that through the entire process, now we can do things like define product requirements digitally, build our design and simulate so that those requirements are met, then come in and build a manufacturing operation, again, on the computer. And now we can do this whole process efficiently, so when we move to the real world, we're guaranteed or at least highly maximize the likelihood that we're going to succeed and minimize that risk. So how does that impact simulation then? So simulation is part of that digital thread, or ties into the digital thread, and we talk about it in the frame of predictive engineering analytics. So predictive engineering analytics, when I talk about that, it's really taking any kind of simulation data, so whether it's 1D system simulation or 3D, like structural, thermal, acoustic, that kind of simulation, or CFD, and or test data, right? I can take all of the data that's available to me and now use that in an integrated way to provide a performance prediction for my product. So now in a requirements-driven systems engineering process, I can ensure that my requirements are met before the product is ever built. And now if I manage that whole thing in a PLM context, now that provides the traceability, the change and configuration management that's required to really walk through that entire digital thread, all the way from beginning all the way through to the end. And as changes occur, I can reevaluate and see that my requirements are still met as I move through that process. So you can see that simulation is not just about taking, building a model and looking at a stress field and seeing that the stress is okay. It's really should be used in this context, in this day and age, in a much more strategic way. And we talk about that, again, in terms of predictive engineering analytics, and our next generation tool set is built around providing that capability. And if we implement that, then what are we doing? What are the benefits of simulation? As we implement that, we're driving innovation, right? We can explore a much wider range of ideas, look at the feasibility of those ideas really quickly before we ever build a physical part. And then because we're doing that in the virtual world, we're saving time, we're streamlining the process overall. So now we also reduce cost and we improve quality in the end. So the impact to the business is huge. And I think as this change comes at us at a really increasing pace, we're going to need those benefits in order to effectively engineer our products. So with that brief introduction, I want to turn it over to Ravi. Ravi's going to go into a little more detail about the use of simulation and some case studies, and then I'll pick it up at the end with one more example and a conclusion. Ravi?
Yes, thank you, Tom. So as you listen to Tom, he very well explained what is the role of digitalization and what does a digital twin mean. However, he also explained that a digital twin may have various different aspects of it, and the one important aspect that we are going to look at today is the simulation aspect. So be it one-dimensional, three-dimensional, everything that is physics-based. And what I am going to try to do is essentially go through a few examples and case studies and show you how this helps you do your engineering in a much better fashion. But before we go that, we of course have to look at what are the challenges that are shaping, the food process engineering. Sustainability, a lot of small brands that are coming up, demand from consumers regarding augmented transparency as well as a digital foodscape. These are some of the trends reported by leading food engineering magazines. And some of them are extremely important. For example, sustainability, precise source and choice of the ingredients, consumers are demanding that, and that means that there are changes to the traditional production processes. The micro brands, they are always coming out with innovative products, which means that you need to have a shortened time to market by doing a faster scale up from anything that is invented in the lab, taking it to production. Similarly, taste, texture, quality, safety, shelf life, all of these are quite important in the way the final product turns out, as well as some other aspects such as packaging and customer experience. How will, for example, a ketchup that I'm dispensing feel while I'm doing that? And so if we look at these challenges, there are a few ways that one can look at solving these challenges, and a lot of them are related to that aspect of digital twin, which is the manufacturing or the realization or the processing of these. So if you look at things like energy efficiency, simulation provides this insightful thermal performance evaluation and conjugate heat transfer. If you look at the innovation efficiency, which is essentially how can I bring a new food product to the market quickly, one has to look at how virtual prototyping at lab or pilot or a production scale can be used to a certain scale-up criteria. Similarly, process efficiency. Everyone, of course, when talks about reducing the raw material per unit product, as well as the waste that is produced per unit product. So lowering cost and achieving process efficiency in many of these classic unit operations in food process engineering, such as mixing, reaction, mass transport. These are some of the important aspects there. And so what we talk about today is three-dimensional, one-dimensional, and including test as some of the aspects that build that digital twin. And when we talk about digital twin, essentially what we are trying to do is take that physical representation and convert it into a digital representation, which includes the geometry, the physics, the boundaries that are involved, the material behavior, the process behavior, and so forth. And the key question we always ask is, why do we need to do this? Where does it benefit me? If you take any process, for example, mixing, which would be in fermentation or any other process step, what you look at in physical reality is very much intransparent. And you may have some probes and sensors that essentially give you point information at few locations. But a 3D simulation, a CFD simulation, helps you make that process very transparent. That means it provides you information in a complete 3D space. It's like as if you can look into the heart of that process. And this information, this is the powerful tool that you can use to improve your processes. And these can be applied in various different stages. People use that to either validate a particular design just to see that whether it will work the way it is supposed to work, or to troubleshoot something that is already designed but is not working to the same efficiency as it is expected to. Or the third stage is having some predictive capability that before you design, can you predict what would happen if you wanted to, say, increase the capacity of a particular process, or if you wanted to change temperature, what would be the effect of that in the overall process behavior. And then eventually you can also think about automating that simulation process so that you can explore all various possibilities, both in terms of the design of the process, but also in terms of the operating conditions, which are the crucial part of process engineering. And for those who are not familiar with how does computational fluid dynamics or CFD works, I have just put together a couple of slides that will explain you in a very simple manner. So in our engineering courses, we always learned about that mass, energy, and momentum are conserved. And what we do in terms of CFD simulation is essentially taking these fundamental mass, momentum, energy balances over a given control volume. And we do that using a discretized space and solve them numerically instead of analytically or by hand, because now you are solving many equations. But there are, of course, always constraints in terms of the boundary that is involved. There are always inlet and outlet conditions, for example, flow rates or heat that is being input to a system. as well as operating condition, which could be the rate at which a mixing tank is stirred, or the rate at which you are adding a coolant or a heating fluid through a system, and so forth. And once we have defined this system, essentially what we do is we take that geometry, discretize it, which is called as the mesh. We set up all the required physics models, that means mass, momentum, energy balances. We define those inlet and boundary conditions, and then we let those equations solve. And at the end of it, what we get is a complete 3D picture of what goes on inside. And once that is done, we perform analysis to evaluate all the variables of concern, which could be concentrations and mass fractions or mole fractions of various species. If there are any particles involved, we can look at how these particles move through the system. A lot of time, turbulence and mixing is important. Food products could be shear sensitive, and you might be concerned about too much shear or too less shear being not sufficient for the process that is looked at. And many food processing operations will involve some sort of heat transfer at a given point. And too less or too high heat transfer can always mean a compromised quality of the product that is produced. So once we have looked at this fundamental of how computational fluid dynamics and particle flows work, let us take a look at least a few application areas and examples. So some of the applications areas that I want to talk about are mentioned here in a brief manner, and the examples later will be somewhat in detail. So for example, any general flow through process systems where you're looking at uniformity of a product, assuring even distribution, even achieving reduction in pressure losses, these are very common occurrences. We also see in many cases where you want to explore various designs through a rapid virtual prototyping sort of system. In this animation, if you're able to see it, shows you various design of a cyclone separator that we explored. And the reason behind is that we want to increase the efficiency of the cyclone separator, but at the same time want to minimize the pressure loss and thus the operating cost of it. Similarly, some specific things such as spray drying or not just coffee roasting, but roasting of many other food material are some of the important application areas. Mixing in that is also very common. Any food processing will always involve more than one ingredient that you put into a tank, and then it needs to be mixed in a shortest possible time in the best possible manner. And this process can consume a lot of power. Uniformity of the blend can play a big role, and reducing pressure losses through the system can also be important. So mixing forms a very broad application area in this example. A lot of the fluid flows and solid flows in food processing can have very non-Newtonian behavior, highly viscous fluids or fluids with elastic properties and so forth. So CFD simulation allows you to look at into detail of how these processes behave. And some of the other things that we can look at are related to packaging. So once you have your product in a packaging stage, there might be a lot of issues which are related to filling, dispensing, as well as maintaining sterilized environments. So let us take a look at least a few of those in a little bit more detail. We'll talk about some of these success stories and examples. So the first one that we are talking about here is related to spray drying. We all know that spray drying is very commonly used in food processing, either for milk powders or coffee powders and similar food ingredients. The way the spray dryer works, of course, is you inject a liquid spray, and as it flows down a vessel that is maintained at high temperatures, the liquid evaporates, and then you get powder at the bottom of the vessel, which then needs to be separated using cyclone separators. So some requirements in this process are related to the residence time of the particles that is required to achieve the desired dried product moisture level, as well as the temperature to which they are exposed. And many questions always come up, such as what happens if I change the feed composition, or if I want to increase my throughput, or if I change the gas temperature, will the product be of the same quality? Would I encounter burnout issues and so forth? There are other design questions such as which atomizer would be the best one to use. So this sort of model needs to include a very accurate heat transfer as well as mass transfer, and sometimes also reactions on the surface of the droplets. And many companies have been using simulation to achieve this type of efficiency in their processes. This example here is showing you how simulation was used to optimize the airflow and the spray injection nozzle. So essentially what you see in this middle picture here is the details of how the spray spreads. And then on the picture on the right, what you're looking at are the simulation results showing you the temperature and the residence time distribution in the dryer. And once you know this distribution and then you know the residence times, you can back calculate how the distribution of each particle with respect to the temperature exposure has been. And by actively using CFD, this company has been able to improve the understanding of this complex physics and use that in doing virtual prototyping. You can imagine spray dryers are large equipment, so they're not something that you can build and test that easily. I earlier talked about rheology being an important aspect. That means there are many cases where you have one or more liquid that is behaving in a non-Newtonian fashion, and then you are looking at how flow of either one or more of these liquids will change and alter the way they can be extruded out through various different nozzle types, nozzle shapes, or equipment. For example, pasta making is a very unique such example where you extrude the dough through many nozzles and giving it the final shape. And there are many operational considerations such as a uniform distribution to all the nozzles, that there are no stagnant areas, that the energy consumption in these nozzles is minimum, which is directly related to the operational cost. And there are also many product quality considerations, such as high shear or high temperature can cause damage to the nutritional value as well as texture and taste and color of the pasta that is extruded. So simulation gives you a very clear idea or a picture about how this process is functioning, and then allows you to take the necessary steps, engineering steps, to remedy the situation if it is not optimum. In such situations, of course, we are dealing with materials of very extreme viscosity, so even 1,000,000 times higher than that of water, and you want to assess if there can be material damage during the processing. And this is always coupled with heat dissipation and thermal degradation. So in our simulation models, one has the capability to include all of this physics in a coherent manner, or in a coupled manner, so that you can understand the complete behavior of such systems. In many processing applications, of course, there are steps such as drying and refrigeration that are involved. So be it air blast cooling or vacuum cooling, one is always considered about, for example, heat and moisture transfer. Here I talk about example from meat processing, where weight loss can occur due to moisture, and a certain moisture level is always important or necessary to be maintained. And then the flow of the air surrounding those food products can have a severe effect on how this moisture transfer occurs. In some other cases, it could be related to sterilization. So, for example, excessive heating can degrade food quality, and therefore the temperature uniformity is important. We have also examples where you can look at the diffusion rates inside a given sterilized environment to make sure that the quantity or the load of germs or bacteria that could diffuse through are below the required regulatory limits. Now, when we talk about food processing, there are always solid particles or solid material that is involved. And so we provide capabilities that can handle such complex particle flows as well. Many snacks and products are used in such a way that they are either coated with seasonings or sugar or caramel or other such products. And then one needs to really look at how the uniformity of this coating is, as well as their residence and temperature exposures during those coating processes. So the discrete element modeling capability, or the DEM capability, essentially allows you to look at modeling each and individual particle. And then this particle modeling can be coupled with heat transfer as well as any spray or other material that is introduced into this domain. We also know that many oil products that are produced in the food industry, they go through a step such as a screw press or an expeller, which means that you are trying to extract the liquid out from a solid particle. And many design and rating parameters essentially depend on this material. That means if you have a given press, it may work well for a given type of particle, but it may not work for a different type of particle. And in those cases, then you need to understand really how the forces exerted by this expeller press affect the overall efficiency of the liquid extraction, and how does it affect the power requirements. So coupling the motion in here together with the particle flow and then analyzing the forces that are exerted on the particles can give you the necessary calibration and extraction force to size these type of machines correctly or operate them correctly in achieving the efficiencies that you need. I earlier also mentioned about coffee roasting. So this is one example where we are looking at a coffee roaster where the particles flow from the top and then they reside here in this roasting area for a long time. And then you also see the flow of the heating media, which is a gas, passing through that roaster. And you're looking at how the temperature profiles are. Now, if you imagine that if some portion of this roaster gets a temperature that is much higher than the necessary temperature, then it would mean that it would degrade and completely change the taste of the coffee beans that come out. So having an extreme uniformity in temperature is very, very important. And the way we achieve this, of course, is that we couple the flow of the heating media and the flow of particles together with the heat transfer, which can give you a complete distribution of how each and individual particle is heated. And that then can help you design or operate the equipment in a manner that you get that necessary uniformity. I also talked about coating earlier. This is looking at coating in a very different type of equipment where you use a rotary drum or a fluidized bed. In both the cases, the principle remains essentially the same. You have a liquid that is injected into the equipment containing the particles. The liquid is then supposed to coat those particles, and then depending on the speed of rotation, the design of that equipment, if there are any baffles that are used to mix the particles, and then exposure of the particles to the spray cone, all of these essentially define what quality of coating you would get. With the help of simulation, you are essentially able to take any information or knowledge that you have, which is more qualitative based, into more quantitative based. And this quantitative basis essentially allows you to design and operate those equipment more efficiently. Now, all of food processing operations have safety as a paramount parameter, and especially when one is looking at packaging and filling, maintaining an environment that is safe and sterile is very, very important. So we have also looked at applying computational fluid dynamics to filling behavior of bottles and other type of equipment as well. So just from the cost perspective, the speed of filling, avoiding too much of foaming, and minimum consumption of inert gas, these are some of the design targets. But from operation point of view, how does a certain shape of the bottle affect the filling rate, the position of the injector, the working pressure, and the duration of that injection? All of these are affecting the way the operation, whether it works efficiently or not. So one can very accurately look at, for example, oxygen or any other gas that is used in the process, whether it gets trapped inside the bottle, and if the bottle product is, or it can be a cause of degradation over, for example, in this case, wine, over time. And then we can look at if we use an inert gas to prevent that to happen, how much and at what rate this inert injection should be designed and operated at. Similarly, we looked at some non-Newtonian behavior earlier as well. This is an example which is showing the filling of a highly viscous food product, mayonnaise in this case. And what you look at is as the nozzle is filling that bottle, it may leave some air gaps around the corners or right below where there are curves, bends, or edges, and so forth. And if there is oxygen or any other gas that gets trapped in, that can cause degradation. So simulation helps you not only visualize but also quantify what is the amount of that gaps that are left, and then you can use that to remedy the situation by looking at if a different filling rate would alter that situation, or if a different nozzle would give you a better performance. I will go through just two last examples. These are very nice to look at, but they also serve a quantitative purpose. So this one, if you can see it on your screen, is essentially looking at dipping of an ice cream cone in a chocolate. So that is the fun part of how nice it looks, but the quantitative part of this is essentially looking at what kind of film thickness do I get on that ice cream cone, and what are the temperatures that are involved, what is the volume fraction of the chocolate dipping that is caused. And this may have a big consequence because, for example, if that thickness of the coated film is too thick, then it might be not a good experience for the person who is consuming this. Or if the film is too thin, then it may break off rather quickly. So such an analysis can give you a complete insight into designing this product so that it gives a very good experience to the consumer of that food product. So we have looked at quite a lot of examples that involved 3D simulation, which means computational fluid dynamics, as well as particle flows using discrete element modeling methods. The Sim Center, which essentially combines all these different aspects of simulation, is summarized over a few slides here. The portion that I was talking about all this time is related to the CFD and DEM simulation, which includes particle flows and fluid flows, coupled with heat transfer and reactions. And the other elements, which is the 3D and the 1D simulation, I'm going to pass it back to Tom, who is going to go through a short overview and then a few examples related to how those type of simulations can also be applied for food process engineering.
Okay. Thanks, Ravi. So as Ravi mentioned, we started off with a little bit of the digitalization message and then the predictive engineering analytics. So SimCenter is the Siemens answer for that predictive engineering analytics. And I don't want to talk or turn this into a product pitch, but I want to talk a little bit about, Ravi showed examples from the CFD end. As he mentioned, and that deals inherently with the flows occurring through the food processing operations. There are also all kinds of other 3D applications that we can do. I'm not going to focus there for now, but things like even not even related to the food processing, right? It might be a food device like acoustics on a blender. one of the number one complaints on a blender by consumers is how much noise it generates. And it's not even how much noise necessarily. If any of you that are old enough to remember the old-timey blackboard, right? Your fingernails going down the blackboard may not be that loud, but the sound quality of that is really terrible. So it's not only acoustics, but sound quality, which you can simulate as well. But then from a 3D end, then you can do things like the structural, the dynamics, all those kind of things. I think I had an animation earlier that I didn't really talk to, but it showed a top load of a bottle, and also a can opening, those kind of things. So there's a wide range of multi-physics, multi-domain kind of things that you can do in the 3D world. Now, on the 1D end, Adam, my slide went away. I don't know if that's visible for everybody or not. Oh, there we went. So on the 1D end, what we can do, it's a little bit different, right? So the 3D starts from CAD. You have a very detailed description of the part. 1D, on the other hand, is a system level simulation or lumped parameter kind of simulation. And what we can do then is model a whole system in its entirety. So this is typically multi-domain and involves a lot of interacting components that could be mechanical, electrical, hydraulic, all those kind of things. And now we can innovate way in advance of having CAD available by putting models together of the whole system, and including the controls piece, by the way. So now anybody involved in designing controls can write the controls in Simulink or whatever you might use, marry that to a 1D system model, and now look at how the whole system performs together. So I think of this kind of tool almost like a multi-physics GUI, right? So very easy to use, very simple to use. So in this case, we've got libraries of things like hydraulic components, pneumatic components, thermal libraries, electrical libraries, mechanical libraries. So if I wanted to build a hydraulic system, for example, I would just go into that library and drag and drop a pump, drag and drop a line, drag and drop a valve, and maybe a tank. And I just quickly build up my hydraulic system, and I input parameters relating to those components, and now all the physics are baked in. So now, as I indicated, now I can look at all kinds of things about the system and really do a lot of innovative kind of explorations. And this is one, we saw the example that Ravi put up of the mayonnaise being filled. So the focus in that problem was on the fluid and how it filled the container. So you're using CFD for that. In this case, Ronki Mario, they make the machines that do the filling, and they need to be able to design those very efficiently, and especially when their customers have all kinds of different container shapes, sizes, whatever, and so they're in the business of designing these customized filling machines. And what they do here, typically what they had done previous to using simulation was you can think of it almost like a make and break kind of approach, right? Where they make a prototype, they run it through its paces, it doesn't meet the design requirements, so they tweak the prototype, remake it, try it again. Very time consuming, very slow, and obviously, you're limited as to the number of things you can try. In this case now, once they were using simulation, they're able to build the whole system. So the mechanical components that are moving, the hydraulic system, the whole thing together with the control algorithms, and now they're able to go through and make sure that you're looking at things like throughput, at the fill quality, how much time does it take to fill, are you fill quality in this case would be more concerned with maintaining a fixed pressure drop, so you get a given volume of fluid in a given period of time. But you're able to go through now and look at energy efficiency, look at all the things that impact that design. And now they credited that with reducing the number of prototypes by more than 20%. They had much better designs, much more innovative, and even made things that were that saved on maintenance efforts. So, the quality of the product that they're delivering to their customers is much better, and they're able to do it faster and cheaper. And that's really what simulation is all about, right? Is providing that ability to really impact and go, that we saw as required through that digitalization process. So I'm gonna wrap up then. We've talked about the impact of digitalization, and it's really real, and it's real in the food industry. And so you really need to think about using simulation, if you're not today, in a very strategic way for the organization. It should be part of the engineering process, and it delivers, real design impact, right? It makes a difference. It makes things more innovative, lower cost, better performing, and really is effective in driving excellence in the product development process. So with that, Deborah, I'll turn it back over to you, maybe for some questions.
Absolutely. Well, thank you so much, Ravi and Tom, for a really informative, fascinating presentation, I thought. So now what I'd like to do is I'd like to open the floor for questions. If you have not done so already, please submit your questions for our presenters today, and we will try to get through as many of them as possible. But for right now, I'd like to start with some of the questions that have already been submitted. So for Ravi and Tom, can you comment on the expertise required to do the simulation, the in-house expertise at a company that would be required to do this type of thing?
Ravi, you want me to take that one?
Yes, go ahead.
Sure, okay. So I would say it varies quite a bit. In the examples that Ravi showed, the computational fluid dynamics typically requires a little more expertise. But I think to use simulation effectively, I think the technologies have come to the point where it's really driven the expertise requirements down. There are a lot of tools that Siemens provides and others provide that are even built into and built for designers that cater to people with less expertise. So I think the expertise required, it has really come down over the years, number one. And number two, the ability to do much more in terms of different types of simulation that are really required in most products. That expertise has come down as well. So you can do more faster simulations, and then the system level simulations are very easy to use as well, and can be, they can be very simple kind of models or very, very refined, and anything in between. So you get a lot of good information without necessarily having to spend a lot of time on the expertise end. Ravi, anything to add on your end?
Yes, just a couple of things. So what you said is absolutely right. Some additional things are that expertise needs some investment and learning, and that's fine as long as the returns on that are multiple times the investment that you make into it. And we help with that in the sense that we have basic trainings, advanced trainings. We have what is called as a project path outline that we engage with the users in terms of outlining what are the goals that need to be achieved in a given time, and our technical support work with them to help them achieve those goals in a timely fashion.
Great. Kind of building on that, so say a company that hasn't used simulation in a strategic way, how should they go about introducing simulation, and then how should they think about using it effectively for product design?
Yeah, I think we've got a lot of experience, and I've helped companies with exactly that for a number of years now. And I typically approach it in a kind of a systematic way, right? You want to look and see, how is simulation used? Is it not used at all? Is it kind of, maybe one guy off in a corner kind of doing it when he wants to? How is it used? What types of problems are really encountered through the development process? So what kinds of simulations should be done? And so typically what we'll do is go in and do, people call it different things, process audit, or, just look at how the engineering process proceeds and who the different customers are of different groups within the organization as it goes. And then, we have a lot of experience in working with a lot of different companies, so we know kind of what the state of the state is pretty well. So typically that audit will help identify gaps relative to other companies in the industry. And then what we do is take and develop a roadmap, and we typically try to make that business-oriented, if you will, so that we focus on things that are going to have a high return first. So we build a roadmap of activity that would help close gaps and ensure that you're using simulation in a strategic way. But that's done in a way that makes business sense. So you wouldn't have to go in and invest, millions of dollars right at the bat, getting people trained and getting tools and doing all that. You invest over time in a way that makes business sense, and that has the maximum impact on the business overall as you proceed. Ravi, anything to add?
Yes, I think that's all correct. Just some practical aspects of this is obviously take up a project, outline what are the goals to be achieved, see what makes sense doing it in-house or even having it done through a consultant or a service provider like we do. And then once you achieve a small success, build on that to bigger successes.
Mm-hmm. I see. And I see somebody, one of our viewers during the presentation was asking about if the software is ready already, or is it developed for each specific process on demand?
Oh no, so these are commercially available tools that and SimCenter is the Siemens brand name for addressing predictive engineering analytics. So it is commercial off the shelf software that has the full 1D and controls, all of the 3D, including just a whole host of domains. So pretty much any analysis that you would want to do, you could do from within SimCenter, including the CFD. And then one of the things that I think is unique with us as well, you're not going to get rid of tests. Just because you do simulation does not mean you will never do testing again. You'll always do tests. It's just used differently. It's used to benchmark products. Maybe you've got a marketing requirement to be the quietest blender on the market or whatever it might be. Well, you need to go off and benchmark what your competition is so that you can turn that into an engineering target. It's used to determine, to validate and correlate models so that you ensure the accuracy of your predictions. So Siemens integrates the 1D, the 3D, and the test, and provides the ability to kind of go back and forth and use one tool in combination with another, or as an augmentation to make sure that the accuracy is there.
I see. Ravi, did you want to add anything to that?
Yes, just 2 bits. So, like Tom said, you will use tests differently, which essentially means that instead of trying to do hundreds of tests, you would perhaps do a lot of them virtually. You would narrow down exactly which tests you want to do, and then you would reduce the number of tests that you would do. So essentially making it the best use of simulation and test in a combination of one another. And in terms of whether this is a ready software, you have to think of it as a box of Legos, if you will, where you have all these different models that are available, but for a given shape to emerge, you take the necessary ones and put them together. That essentially reflects the process that you're trying to model.
I see. Great. Thank you so much. This was talked about a little bit in the presentation, but I was wondering if you could expand on it a little bit more. The mixing tank simulations, how can the simulations help in a mixing tank application?
Yes, that's a good question. So this is one of the most widely used and critical area in food processing, as well as other processing applications, including pharma and so forth. And if you imagine, most of these processes, they essentially have more than one raw ingredient or raw material that goes into the process, which then needs to be mixed to produce the final product. And this means that you need to mix them the most efficiently, so that each and every molecule of one species mixes with the other species. So the way we do our mixing simulations, we have a very easy to use front-end setup where people can drag and drop some of the common mixing elements, define their geometries very quickly. And it also allows you to look at even more than one phases. So you may mix a liquid with a solid, a liquid with a liquid, or a solid with a solid. So all those types of combinations are possible. And then at the end of this, what you get is essentially looking at what is the power consumed, what is the efficiency of mixing for these different impellers you might use, how does that change with time. All that type of analysis is possible.
Wow, valuable information for sure. Okay, so and then I think you touched on this a little bit as well, but if you could explain it a little bit more, the type of models that are available to simulate a given system.
Yeah, I'm not really clear on the intent of that one, but I think the types of models. So in terms of domains that we can simulate, if I look at it from that end, there are there's structural, and that can be linear and nonlinear. There's thermal. There's dynamics. With either dynamic response kind of things or vibration-oriented kinds of solutions. There's acoustics, multiple types of acoustic solvers. So there's boundary element methods and finite element methods, depending on the frequency range and the type of problem that you're looking to solve. There's multi-body dynamics for looking at moving pieces of equipment, any kind of mechanism that moves back and forth. You can model that, including with flex bodies, by the way, to pick up structural kinds of like stresses and that kind of thing in a moving body. Fatigue kind of simulation. So there's this whole range, literally about everything you would want to do, including EMF kinds of applications and that kind of thing. And of course on the CFD end as well. But then and the CFD includes all kinds of physical disciplines as well. So heat transfer, the chemical processing, all kinds of different applications on that side as well. So if that was what was meant by models, there's a whole range of domains that are available. It's typically finite element methods for most of them, maybe finite volume as well, but then boundary element methods if that's what was meant by type of model. And then of course the 1D is what's considered a lumped parameter kind of approach. So it's not based on CAD. it's a bulk representation of a mechanism or a part or part of the system. So I'm not sure if I answered that question, but Ravi, I'll let you take a stab at it too, and see if you had any different interpretation there.
No, I think it's my interpretation is very close to yours. So the Sim Center has multiple different tools, and each of these tools essentially can do various different aspects of the physics that one is involved in. Like Tom explained, it could be acoustic, or it could be vibration, or it could be mechanical, or it could be fluid flow and heat transfer. And then within each tool, you will have certain options that you can use to include the relevant physics that is of interest. So, for example, in CFD, if you are doing mixing, you might say that in my problem, mixing two liquids is what is sufficient, and that's what I will use. In somebody else's problem, there might be heating that is essential, and you can include heat transfer in it. And so you have this choice of making the right picks for the various capabilities in terms of physics.
Yeah,
Wow.
and maybe just adding like one comment there too. We can also, in addition to these different domains, we can also co-simulate with the different tools. So, for example, in that mixing machine or the filling machine that I showed modeled in 1D, Ravi showed the CFD kind of example that was similar, but filling that mayonnaise jar. Well, if you wanted to, you can even couple the two together. So now you get a very detailed look of the system and the controls, but then you also get a very detailed view from the CFD end in terms of that quality of fill that Ravi showed on the mayonnaise. So you can mix and match those, and that includes even test models. So you can get, for example, if you're looking at a dynamics-related problem, you can get a modal model from test and marry that to a finite element model of a part of interest, and now you get the dynamics of the full system in a much reduced degree of freedom manner. So it solves way faster, but you get all the dynamics of the overall structure, but you're able to window in on a part of interest. Maybe it's a part that has a high stress. You're worried about the stress levels or something like that, but you can window in and do that. So that there's a way to mix and match these models in addition to what we discussed.
Wow. Fascinating. Well, thank you so much. That's all the time that we have for questions today, unfortunately, but please join me in thanking Dr. Ravi Aghlavi and Tom Phillips for their great presentation, as well as our sponsor, Siemens. If you have any additional questions or comments, please don't hesitate to click the Email Us button on the console. As you exit today's webinar, please take a couple of minutes to complete our survey. We strongly welcome your detailed comments, and please visit www.foodengineeringmag.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience. Have a good afternoon.